Welcome back, and this is the third and final video in Bootcamp 1, Module 2, Managing Data. We've just done some subsetting of data using Boolean operators, and now we're going to practice with some of that subsetting and do some other subsetting operations and data management operations using a new data set. So this new data set you should have downloaded at the end of the previous video. It's the turtle data set, so if you haven't done it already, just save this into your project directory so we can read it in and get started. So let's move over to our studio. All right. Let's go to where we left off, where it says practice subsetting a data frame. And just make sure in your files tab here that the turtles data is in your working directory. That means you can access it without specifying the exact file location, just specifying the file name. So let's first read it in using the read table function. And note that we're using read table and not read.csv to read this file in. And also, you might see that there's no sep equals to define what the separator is. Let's look at the turtle data file and just remind ourselves what it looks like. And we see that it is tab delimited, and we can go back here and just know that the default for read.table is that the delimiter would be space or tab delimited. So if we type in question mark read table, we can find that out. So here, let's make this a little bigger. And if you see sep equals open close parenthesis, and recall that the open close parenthesis allows for any kind of space delimited file, or reading in any space delimited file. That's the default because you see that it is in the read table function. That is after this equals sign, meaning that the default header, for instance, is false. All of these, after this equals sign, all of these are the defaults for the function. And if you wanted to read more about the separator, you can learn more about those defaults. So the field separator character values on each line of the file are separated by whatever character you specify in this sep argument. The default, the separator, is white space. That is spaces, tabs, new lines, or carriage returns. So that gives you the answer. So sometimes you have to dig kind of deep to figure out what a function is really doing, but usually the information is in this help file. So if you were confused by this line and why it didn't have a sep equals argument, you can go in and figure out why and what the default is for any arguments. Not all arguments have defaults, but you can easily find them by using the help file. All right, let's get back to this. Let's read in the turtle data file. And now we can look at the turtle data. Here's the whole data set. There's a few missing data. That's the first time that we've seen missing data in this bootcamp so far, but in real data sets, missing data are often an issue. And we have a number of data on each of these unique turtles. We have their sex, we have their carapace length, that's just their shell length. We have their head width and their body weight. All right. We can find out more. In general, the first time when we just open up a new data set, we want to explore it. We want to, just do some summaries. This is the column names. This is the first few lines. We could do a summary and get more information about each of the columns and what information they contain. All right, we've been working with subsetting. So let's do a subsetting operation and just figure out, actually what we're going to do is make a new data frame that is a subset of the full turtles data frame, but it just contains the female turtles. So let's look at what we're doing here. We're first going to take the sex column, which looks like this. All right. And we have some NAs, we have some female, we have some male. You might also note that there's some that are kind of mistyped. We'll get to that later. But most of the females are fully typed out with the full word female. Okay, so we're going to take that vector and we're going to do a Boolean operation, and we're going to ask element-wise by element. So for each element in this vector, for element 1, 2, 3, 4, 5, for each one, we're going to ask, is it equal to female? Does it match this text string? And it'll return a vector of true and false, and NAs in the case of missing data. NA just means not applicable, and that is R's internal representation of missing data. Next, we wrap that into the which function, which takes that vector of trues and falses and NAs and returns the indices that are true. All right, so that gives us a set of indices that represent, where the trues are in this vector. We take that list and use that to specify the rows of turtles.df that we want to retain in this subset that just represents females. So we take that, and that returns a data frame with just the females. And then we store that in an object called female turtles.df. So in this one line, there's a lot of functions being called and a lot going on. So I just wanted to go through that real quick. Let's run that line. Now we have a data frame of female turtles. Another thing we might want to do with data in general is to take summary statistics on a subset of observations. One way we can do that is, again, just using this which operator. So here, again, we're going to take just the females. This is the set of indices representing females. And this time we're going to take the weight column and just take the weight of individuals that are female. And that's going to look like this. If I run just this part, it's going to be the weight of all the females, and we can take the mean of that. Now, of course, since we already made a subset data frame of just females, we could just take the mean of that new data set for the weight, and we'll get the same answer. All right. Let's get back to the sex variable, because we noticed that there was an issue here. If we'd use this unique function that just gives us all the unique values in turtles.df $sex, which is the sex column, and we see that there's not just two sex designations. There's male, female, and there's NA, meaning it's unknown if it's male or female, and then there's this other designation, FEM, which is probably a typo. We should assume that FEM is the same as female, and we should represent them in the exact same way. So that often happens in data sets. There's a data entry error, and you have to go in and fix it. So let's use Boolean operators to fix that issue. All right. And here we can use this table function. Table just takes a set of categorical representations like male and female and just counts up the number of observations that meet each of those labels. So we have one turtle that's labeled FEM. We have 7 that are female and 7 that are male. Let's really combine the female and FEM. So there should be 8 females total. All right. So we're going to use this Boolean operator. We're going to just determine which of the turtles has that FEM designation. And we see that that is right here. We use the which function to determine the index of that observation, and we'll use that to take the row to specify the row for that individual, and 2 is the number of the column that represents sex. And so if we run this whole line, we will see that that evaluates to the label for the mislabeled sex, female, in the data frame. We can then use the assignment operator to correct that. So here we're specifying the place in the data frame where the incorrect data is stored, and then we're correcting it using the assignment operator. So we're changing this, which evaluates to FEM, we're changing that to this full text string, female. And when we do that and we rerun this table command, we see that the FEM no longer exists. We just have female and male and some NAs. All right. Now, there's another function, a convenience function that R provides that allows us to do these kind of operations even easier, but I think it's useful to go through, the use of the Boolean operators because they're really flexible and really important to get a good grip on. But let's use the subset function now to do some of the same operations we just did. And remember that redundancy is an aspect of most programming languages, and it's a great aspect because it allows us to never get stuck because we always have some way to do something. So, subset operator. Subset is just a convenience function that allows us to take a data frame and subset it according to some criterion. So basically what this does is it says, okay, I want the subset of the turtles.df data frame. So the first argument to the subset function is a data frame, and then you specify that you want only those rows where the column sex is equal to this text string female. So we've already done this operation, but this is a simpler way to do it. So if we run this, it just gives us the data frame. It returns a data frame, but just with the observations that are female. So we can then store that in a new object called female.turtles, and we've done basically the same thing, but with fewer characters. Another way to do it is we could say we'll take the subset of this data frame where the sex is not equal to male. Let's see what happens there. It's the same thing. Another way to do it is using just the Boolean operator. We take those observations where the sex is not equal to male and use the which function and get the subset. So we can get the same subset many different ways, and there you go. Key feature of programming, lots of ways to do things. All right, here's another subset. We're going to take a subset of the turtles data set where the weight is greater than or equal to 10. And let's just look at the weight variable, turtles.df weight. So we should get several of these. If we ask the question, if we query using a Boolean query, is the weight greater than or equal to 10? False, true, false, 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 etc. So let's run that and get the subset of turtles that weigh more than, greater than, or equal to 10. And here we go. All right. Now, just continuing on this theme of managing and sort of correcting data errors, which happens a lot. Let's imagine there's a couple observations here, or a couple individuals, I should say, tag IDs. So that first column of the turtles.df is a tag ID. It kind of gives a unique identifier for every individual. So now we're going to specify that we know that there are some observations that are funky or weird, or maybe we want to correct in some way. So we know that turtle 13 and turtle 105 are bad observations for some reason. All right, so let's first store those in a vector that now we can use later. So we have this bad tags vector, and so now we can use that to subset and make corrections that we might want to do, or if we want to just eliminate them entirely from the data set, we can do that. So first thing we're going to do is we're going to use a boolean operator to go through the tag numbers and ask individually, is this in the set of bad tags? And the bad tags are 13 and 105. So basically asking, is this either 13 or 105? No. So false, 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 false. This one's going to be true, and this one's going to be true here. So there's going to be a couple trues. So if we run this Boolean query, we'll get a couple trues. Remember, if we use the exclamation point, we reverse the trues and falses. So this is going to be those observations that are not members of the bad set. And those are the good set. And so that is, we're going to use those to, those indices, basically, the ones that are true, to represent the good turtles, the ones that we want to keep because they're good observations. Those are the rows we want to keep. We'll keep the column blank because we want to like keep all the columns. So we now make our own data frame for the good turtles and the bad turtles. So we separate out the good and the bad. And if we look at the bad turtles now, we see that they're just these bad tag numbers. And we could either throw that out or we could, correct the bad data, whatever. But this just allows us to work with our data and make sure that everything's good before we move on to the data visualization and analyses and so on. So this is just a typical step, and the Boolean operators really help us in making that happen. All right. We can do some data manipulation using subsetting. We've already seen some of this. So imagine we want to take all turtles with weight 5 or heavier and set their length to, let's say that this represents an adult turtle. Anything that weighs 5 or greater is adult, and we're just going to set the length of those turtles to 48. Now, I don't know exactly why we're doing this, but you can maybe imagine a scenario where this would be a useful thing to do, and there are lots of similar type operations that you'll be running. So first we're going to take this weight vector, and we're going to just figure out which of those weigh greater than or equal to 5, and that's going to evaluate to a vector of indices. And for all of those indices, we're going to set the length variable. So we're going to set the length, but only the length of those individuals that weigh more than 5 or greater than or equal to 5. We're going to set the length to 48. So we see that. Let's just run this first part to see what the length of those turtles actually are. They vary from 41, 40, up to 48. We're going to set all of them to 48. If we use this equal sign, or if we use the assignment operator, either way, it'll assign those values to be equal to 48. And now we see that there should be a bunch of 48s when we run this vector. This vector is now full of 48s. All right. Another thing we can do, we can take turtles that weigh greater than or equal to 6, for instance. Here here's a vector of true or false. True means greater than or equal to 6. And we'll take we're going to make a new variable, because this doesn't exist, right? Yeah, we haven't created this yet. And, to be even more explicit, let's first make a new variable. So what we're going to do is make a size class variable. So we're going to kind of transform this weight variable to just 2 size classes, either greater than or equal to 6 or less than 6. And we're going to make a new column of our data frame. So turtles.df size class. It doesn't exist now. Whoops, that's turtles.df. It should be null. It doesn't exist now, but we can make it exist. And if we just say equal to NA, it's just going to create a new column of all missing data. And I like to do that before I add data to a new column. So now if you look at turtles.df, there's this final column called size class, but it's all missing. Now we can start assigning that variable. So first we're going to assign that variable for all turtles that weigh greater than or equal to 6. We're going to assign that to be size class 1, meaning adult, for instance, and we're going to assign all the turtles that weigh less than 6 to size class 2, which represents juveniles. So let's run those lines. And then if we look at the size class variable, it's a bunch of 1s and 2s representing juveniles and adults. And we see that we have an additional column because we had 5 before. Now we have 6 columns in turtles.df. All right, that's basically what we wanted to do with subsetting. Let's move on to sorting, because sorting is another important operation that we're going to do frequently. It helps us to look at the data, check the data, make sure there's nothing super weird if we sort from lowest to highest. We'll see if any of the lowest observations are below a realistic value or the highest observations are above a realistic value. So it's a good way to just look at the data and check it, make sure everything looks right. There's a couple functions that are really useful for sorting. One is naturally called sort, and if we want to uncomment this line and this line, we can look at the help files for sort and for order. So if you want to learn more about these really important functions, you can do that. But sometimes it's best to learn just by doing and trying things. So let's try a couple things with sort, and maybe you can figure out what it is that differs between sort and order. So let's continue with the turtles data frame, and we're going to look at this carapace length, which is a quantitative variable, and we've already set the carapace length for larger individuals to 48. So there's a bunch of 48s here, but let's sort it. All right. What did that do? So it literally takes all these elements of this vector and just arranges them in order of, and by default it's from lowest to highest. Now you could look at the sort function help file and see that there's this argument called decreasing, and it has a default. The default for this argument is false, which means that it's by default going to sort in increasing values. But if you said decreasing equals true, then we can sort in reverse order. All right. So just look at the help file if you have any questions about how to use these functions and what their default values for the arguments are. All right. Let's look at order. So we'll do the same thing, but instead of sort, we're going to use order. So this doesn't give us the actual values, because you see that those values are, first of all, they're floating point, they have a decimal, and they are much larger in general than these values. What do these values represent? What is order returning? So what is going on here is it's returning the indices in the proper order. So in other words, if you're going to sort from lowest to highest in this case, because the default for order, just like sort, is sorting from lowest to highest value, the third element in the carapace length vector is the smallest. The 10th element is the next smallest. So let's look at that. So let's first visualize what's in the original carapace length variable. This is what it looks like. And then I will run this order again. So it's saying that the third element in the vector is the smallest. Let's check that. 1, 2, 3. The third element is 24.3. Can you see anything in that vector that's less than 24.3? No, it is the smallest, and then the 10th element should be the next smallest. So 28 should be the next. That's the 10th element, and so on and so forth. So order gives the indices of the correctly ordered vector. So It's slightly different than sort, and it's very, very useful. In fact, it's more useful than sort for almost all the operations that you're going to do in R for sorting. So if you're going to sort a data frame by one column or vector, we're going to use order, because what we're going to do is, if we want to sort this data frame by the tag ID number, for instance, we'll take this tag ID column and we're going to define the indices in the order that that properly order the vector of tag IDs from lowest to highest. All right. So the 20th ID is the smallest one, followed by the 3rd and the 6th and the 7th and 8th, and so on and so forth. All right. And we're going to use those to define the rows of our new data frame. So we're going to basically we're going to take the turtles.df data frame and we're going to reorder it such that the tag number is properly sorted from lowest to highest. And it's going to look like this. So now we've resorted the whole data frame, not just the tag ID, but all of the observations in order of increasing tag ID, which is something that we do all the time in Excel, for instance. And to do it in R, we don't use sort, we use order. And we can save this data frame as a new object called turtles.tag, meaning sorted by tag. And there it is. We can order a data frame in reverse if we want. So we'll take this, we'll basically do the same thing. We'll take this order, but we'll reverse the order. So this just takes a vector and makes the vector backwards. So you can see what it does here. We'll get the results from order, and that goes 23, 6 all the way to the end of 16, 21, 17. If we reverse it, it'll be 17, 21, 16, so on and so on and so on. So it's literally reverse the numbers in that. And then we'll use those as our row IDs in our new sorted data frame, and we'll have the ID but in reverse order, and there you go. You can do that. Of course, you could also, in the order function, you could say decreasing equals true and sort it in decreasing order. So again, lots of different ways to do things. You can sort a data frame by more than one column, just like you can in Excel. You first sort by ID and then sort by date or something like that. So we can do the same thing in R using the order function. We're first going to sort by sex, and then within sex, we're going to sort by weight. All right, so then it gives us the row IDs that properly sort according to these two variables, sex and then weight. And then we use those as our row IDs, and we can get this whole data frame that's sorted in a proper order. First by sex. So first by sex, it's going to be female, then male, and then NAs. And then within sex, it's going to sort by weight. So the least mass female weighs 4.5, and then 6.2, and so forth. And the lightest male is 3.9, and so on and so forth. And so you can see that it did do what we asked it to do. All right, a common problem that we run into in most data sets is missing data. So let's talk a little bit about how R works with missing data. Before we do that, let's read in a different data set that has missing values. This is a very similar data set to the first data sets that we read in the first video of this lecture. But it's going to have some missing data. So let's go back quickly to the website, and we'll go with a section that says dealing with missing data, and we're going to download a new data set into our project folder or working directory, and let's do that now. So I'm going to save it to my R Bootcamp folder, and it's called data_missing.txt. So once you have saved that into your working directory, go back to our studio and we can start working with missing data. All right. All right, so we're gonna use the read.table because if you go into the folder, into your working directory and open up the data.missing, you'll see that it is indeed tab delimited. So that means that we can't use read.csv. So we'll use read.table to read this data in. We're going to specify the delimiter. In this case, to specify the tab delimiter, you use the \t syntax, and that tells R that it's a tab delimited file. We can try a few different things because, again, the best way to learn is to try things. So let's first read this in and verify that it worked. All right. So we'll run this and see that there are indeed NAs in both the import and export column. So R correctly read these in as missing data. Now, just out of curiosity, what would happen if we didn't specify the tab delimiter? What would happen if we just used the default, which is open close quotes, and that means white space in general, like we've been through. So let's see what happens. It actually did throw an error. So it's missing some elements and it doesn't really know what to do because it doesn't know whether the delimiter should be just white space in general or a tab. So let's go back to the data and see what's really going on here. So data.missing. Let's find a column that has missing data. So it looks like the Dominican Republic has missing data for import. Now we see there's one tab and then there's no number and then another tab and then there's a 14. This whole space here is white space. So when you use the default, it's saying, well, I don't know if there's one or two entries in here, and so I'm going to throw an error because I can't figure that out. So the default is not good enough to pick up missing data many times. So you have to specify the exact delimiter. If it knows that it's a tab delimiter, it sees one tab, missing data, and then another tab. Here it sees tab and then actual data and then another tab. So just be careful with your data set when you're reading it in. R is pretty good at throwing errors when it doesn't know something, but be careful. And oftentimes it's a good idea if you know a data frame a data file is tab delimited, specify that because that will help R determine if there are missing data. All right. So let's go back to the \t for tab, and it reads in no problem, and it gives us the answer. It gives us the right result here in terms of reading in this data set. All right. So there's a few useful helper functions that R provides you for dealing with missing data. We have the NA omit. Let's see what happens when we use NA omit and feed it this data frame with missing data. And we can access the results or print out the results here. And all it does is it gets rid of any row that has an NA. Has it one or more NAs. So that can be useful if you really do want to totally get rid of those observations, but you may not always want to get rid of those observations. You might want to replace the NAs with real data that come from another source. You may want to interpolate those missing data to a value that is the most likely value given other things you know about that observation. So, but this is a convenient helper function, and of course you can learn more about it by using the $na.omit syntax and just getting the help file on that. There's a boolean operator actually that's really useful for NAs, determining if there are any NAs in a vector. So we can use this, and of course you can learn more about it. in fact, learn more about lots of different things that R does with missing data, and that can be a useful help file to read through. Let's see what isNA does, what this function isNA does, and it should return a set of Boolean results, trues and falses, and it indicates for every element of our data frame in this case if it's an NA or not an NA. So most get false because not NA, but there are a couple NAs here. There's a couple for import and a couple for export. All right. We can use the which function with this set of NAs, and note that this set of NAs is actually a matrix. Let's even look at that. I'm not even positive. I think it should be a matrix. So let's look at the class of what we get when we do that. And we get, it is a matrix, all right? So it's a matrix of Booleans. Now, if we use that matrix and put it in the which function, it gives us the, and this is getting confusing, but it gives us the element IDs of the matrix that are missing. But it does it in a kind of funky way because it first converts the matrix into a really long vector, and then it gives us the elements of the vector that are NAs, right? So, oh man. So, you know, if you were to take this and convert it into a vector, this is what R is doing internally. So as vector, and we can put that in. So now we have a list of trues and falses as a vector, and then we can run the which function around that, and we get this set of IDs, 27, 36, and that's the exact same thing that we got here. So you see that R is actually kind of like converting to a vector first, and then getting the IDs. So it can get a little confusing. If you want to get the actual row and column of all the NAs, you have to use another argument to the which function, which is array index is true, and then you get the rows and the column indices of the NAs. And that can be a little easier to interpret. So again, if you wanted to learn more about that, use $which to get more information about the which function. So we're getting a little more advanced here, but I think it's useful to see how this all works, how you can try to understand what's going on in R, how to use the help files, and figure out what R is really doing. All right. Now, one really useful thing is we can use the this Boolean result, trues and falses, trues for NAs, falses for not NAs. We can use that to subset a data frame, but we can also use it to change the values from missing to non-missing. So if we wanted to assign all the missing data values to 0, we could do that. We take this data frame, we're going to just give it this set of trues and falses. Remember what it looks like. It looks like a matrix. And R is going to know that this data frame has the same dimensions as that matrix, and it's going to say, okay, we'll pull out the trues and falses. Those are, we'll pull out the trues, we'll pull out the ones that are NAs. Those are obviously evaluate to NAs, but we can reassign those NAs to be 0. And then we should not have any NAs anymore. We have zeros. Where the NAs used to be, we have zeros. All right. So now there's no more NAs. There's no place for us to go. So let's re-get that data frame back. Missing mean df, and we're going to read the file again using the sep equals tab. All right. And now we have the data frame back with NAs. Let's do another interpolation. This time we're going to replace the missing values of one of the columns, the export column. We're going to replace the NAs with the mean value for the export column. Let's look at this because there's a lot going on in this line. All right. So first, let's just look at this, the right side of the assignment operator. And what happens if we just take the mean of the export column? All right, let's first just get into the console here and look at what happens if you just try to take the mean of the, missing mean df export column. R gives you an NA. And why does R give an NA? Well, because the export column, if you look at it, has some NAs in it. That means that we don't know what the value is. So if we don't know what the value of this is or this is, do we know what the mean of this column is? No, because depending on what the value of those NAs are, the mean will change. So therefore, R is correctly saying that the mean of that vector is unknown because that vector has some NAs in it, so we can't know that. So the mean function does have another argument called na.rm equals true, which means, do you want to remove the NAs before computing the mean? In that case, if you use that argument, you get a result that is the mean after the NAs have been removed. But you have to specify that NARM equals true, because the default for the mean function is that NARM is false, and that is you don't remove the NAs, and therefore you don't know the mean. All right. So now we have, this is the mean after the NAs have been removed. Now what are we doing? So now we're taking this export vector, but we're only subsetting those that have NAs for the export column. So we're only taking those two. We could use the which function if we wanted to, but we don't need to. Remember, R automatically thinks that trues are the ones we want to subset if we give it a vector of trues and falses, but we could also give it the indices that are true, that is 12 and 18. So we're just going to take the 12th and the 18th element of this export vector, and we're going to, which are NAs obviously, and we're going to replace those with 10.2, right? So that's what this whole line is going to do. And then for the export column anyway, we're not going to have any NAs. We still have some NAs for import, and we could do that for import, and that I would encourage you to try that. Try doing the same thing with the import column. Just make sure you understand how to do this. All right. Let's reread the data set back in one more time. There we go. And another useful function for working with data sets with missing data is this complete cases function, and that's going to return the rows of the data frame that are complete, that is, that have no NAs. All right. So it's a boolean operator. It's going to return the rows. It's going to go row by row and to say, does this row have no NAs? True, 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 true. This row happens to have at least one NA, so it's false. It's great for using making a data frame that has kind of cleaning up a data frame, making sure that it doesn't have any NAs. So if you just used this set of trues and falses, this is going to give you the data frame with only rows that don't have NAs. So there shouldn't be any NAs here. Of course, if you use the Boolean reverse operator, the exclamation point, now it's going to give you only those rows that have one or more NA. And we can call that missing.df, and this gives us all the rows that have one or more NA, or missing data. Just note that when you use the summary function, it actually conveniently gives you a summary of the missing data for every row. So when you read in a data frame, you almost always use the summary function to look at the data frame, and one of the nice summaries that it gives you is the number of NAs, right? Of course, you can summarize individual columns as well using the summary function. very flexible and useful. Just a quick note, we've already been through this, I think, but you can use the names function, which is a great way just to get the column names for a data frame. I need to reread the data.df because I started with a fresh data frame. So just bear with me, and I'm going to reread data.df so I have that in there, and then go back here. And remember, you can use the names function to get the names, the column names, but you can also change the column names. So if I wanted to change the names to these briefer names, for instance, I could just change the names of the data frame really easily just using the names function. I could also use the call names. Again, many ways to do things. And I could change the names there, and it goes back to these names. I can also assign row names, which can be useful, and I can show in a second. So now, what I'm going to we haven't seen the paste function yet, but that's a kind of useful way to work with strings and to create strings and automate the creation of strings with regular patterns. So here's the paste function. We're going to paste this string, this string, it's just obs, with this vector, which goes from 1 to the number of rows that we have in our data frame. And we're going to say that the separator is nothing, just a blank, like no spaces at all, nothing. So we're going to paste this OBS string with 1, and then paste it with 2, and then 3. So R knows that since we're giving a whole vector as one of the paste arguments, it's just going to repeat this string the same number of times that we have elements here, so that what we're going to end up with is obs1, obs2, obs3, obs4, and so on and so forth. So the paste function is kind of a useful way to make these regular patterns with strings. And we can now use that as our row names. So we have obs1, obs2, obs3. So we set the row names of our data set to have real names. And we can use the names, the row names, to index if we want. So data.df, and I just want, say, the 10th observation and the 12th observation. So obs 10 and obs 12, and let's say I want all the columns. So now it gives us the 10th and the 12th observation. So sometimes it's nice to have named rows and columns, because now we can really use those to index, and I could use the column names too. So exports and country or something. What did I do? Oh, I mistyped that. So we could use the names. Now, of course, you have to be careful about typing things correctly, because R is not going to be smart enough to know the mistakes you make. Okay, before we end this module, a couple common pitfalls to avoid. One thing I would avoid at all costs is the attach function. You'll see this in example R code that you get from the web. It's useful in some ways, because what it does is it allows you to take a data frame, and we just make a data frame here called df that looks like this. We have two columns, A and B, and if you want to refer to any column within that data frame, you have to go to the effort of typing in df and $sign and getting the A column. And if you attach that data frame using this attach function, you don't need to specify the data frame name anymore, because you can just specify the name of the column. So it's just kind of convenient. Now we have A and B without the df, and you can work with it as if it's an object in your working environment, and you can add 2 or add 1 or whatever to it, and just work with these objects just like you would any other R object. And then, at the end, when you don't need it anymore, you can detach it, and then it no longer exists on your environment, but it does exist within your data frame. So looks convenient, but it really causes more issues than it's worth. It oftentimes, you might forget to detach something. You might try to manipulate something that you've attached, but it doesn't end up in the data frame itself after you detach it. It is really more trouble than it's worth. Just trust me on that. So I would just recommend not using it. I'm not going to go into great detail about why, but it is problematic. Another thing is when you read in data, oftentimes, the default for read.csv and read.table is if there's any character type, column in your data set that you're reading in, it's going to read in automatically as a factor type in R. That can be problematic. And so I would recommend just reading everything in as strings, and then you can convert variables to factor later. But if you're using the base R read.csv function to read the data sets in, I would also recommend using this argument. Strings as factors is false. It's just going to make your life easier in general. So this country column, if I look at it here, it's going to be a set of strings, and you can just see that because it's just every element is enclosed in quotes. It's not a factor. There's no levels associated with this. If I don't use strings as factors, it's false. So I just realized that R has updated. The new version of R doesn't actually have the default be to read strings as factors. That is a totally new thing. So just check this out. So I just learned something. So if you were to do $read.csv, you can learn more about the read CSV function, and in the version 4 of R, they've now changed it. So strings as factors, that argument, is now set according to whatever default you've set for your R in general. Now, there's probably a way to set this default if you want it to be true, but if you run this line, it's false. And so actually, they must have gotten enough complaints about this feature that they've changed the base R so that string data read in as strings, not as factors. So don't worry about that anymore. I'm sorry, I will change the Bootcamp after this to reflect that. But I think it's kind of an interesting note that our versions do change slightly, and it's important to know that. And so you can always use the help, just try things out. You can figure it out on your own eventually once you get comfortable enough with R. All right. Another really quick note before we end is that there is. Maybe R's changed this one too, but let's look at. Okay, we're gonna make a matrix. We'll call it new mat, and this matrix. Let's see what it looks like. So it should. So we're going to fill the matrix in by row. So it's going to be 1, 2, 3, 4, 5, 6. It's going to contain those elements. It's going to have 3 rows, and it's going to be filled in by row. So there we go. 1, 2, 3, 4, 5, 6. And if we wanted to take the first row of new mat, we could do that. We've seen that before. And the class. Okay, so it still does this. Okay, so the class of this is not a matrix anymore, which is kind of weird because the class of new mat is a matrix, right? As it should be. It's got 2 dimensions, rows and columns. Now, when we subset it and take only the first row, it's no longer a matrix. And so if we were to save this as a new variable, so let's save it as A, the class, and just say, what's the class of A? It's integer, it's not a matrix. That means that we can't specify the row and column anymore, right? The first row of that and the first, it's going to error because it's not a matrix, because it only has one dimension, so I can only subset it as a vector and get the elements that way. That's can be a really difficult thing when you're programming and say you don't know whether an index is going to have. So here, for instance, if I take the first and second column, first and second row, and get the class of that, it's a matrix, right? What if I don't know? What if that's a sort of a random thing, that it could be length 2, it could be length 5, but it could be length 1. If it's length 1, the resulting object is a vector. If it's length 2 or more, the resulting object is a matrix. So again, length, length 1, if you just have 1, it's a vector. If you have 2 or more, it's a matrix. That's a programming problem, because if you down the road in your script refer to it with 2 elements and it only has 1, if you refer to it, try to index it with a row and a column, it throws an error and then your whole routine is broken. If that's an issue for you, it's really useful. And I learned this the hard way, but there is a drop equals false argument that prevents this from happening. So if I use drop equals false, even if I have, if I'm only referencing a single row, which could be reduced to a vector, it's still going to be a matrix, and you can still work with it as a matrix. It's just going to be a matrix with 1 row. So if I look at the class there, it is indeed a matrix, and if I were to use drop equals false here, I could refer to it correctly using row and column, and indeed it still is in R being considered a matrix. I'm sorry for that. That may not be super valuable to many of you, but it really screwed me up at one point, so I just want to just get that out there. So thanks for humoring me on that. At this point, I would like you to take some time to work out the challenge problems and make sure that what we've gone through in this module makes sense. And we will pick up next time with plotting, graphics, and statistics, just some real basic stuff on statistics in the next module. So I'll see you then.